Michael, the best way to describe him is to say that he's simply one of the world's experts in paleoclimate. And he's researched, lectured, taught on that topic for 40 years. However, his book for Princeton University Press will, I understand, be actually his first book. Is that true? So we all look forward to that, and that is simply entitled Paleoclimate, and I gather it's in production right now. So, Michael.
Most people in this room would say that we're adding carbon dioxide at a rate that's going to have a significant impact on climate, and likely already has. And so if this is true, there have been major climate changes, as David talked about, over Earth history, and we ought to be able to look at these past climate changes and see the link between CO2 and climate. And people have done a lot of work on this, some of which David showed. The most important work, of course, is the ice core record, where we can actually measure CO2 concentration changes and compare them to climate changes. But that only tells us what was going on over the last 800,000 years or so. And when you try to go beyond that, it gets a lot harder. But anyway, I'm going to talk about this effort. So this slide shows the reasons for variability in the CO2 concentration of the atmosphere. It's not clear that we know all the reasons or we've identified all the important variations, but what this slide represents is a taxonomy of the major CO2 variations that we recognize have occurred over geologic time. And the first of these, which David talked about at some length, are changes in the CO2 concentration of air over timescales of 10 million years or 100 million years or longer, due to the imbalance between the outgassing of CO2 from the Earth's interior and the uptake, or the changing balance between the outgassing of CO2 from the Earth's interior and the uptake by chemical reactions with rocks. Then there are changes over timescales of hundreds of thousands of years and tens of thousands of years. To me, the longer of these changes is simply associated with changes in the carbon cycle on land or in the oceans that lead to burial of more organic carbon and cause there to be less CO2 in the atmosphere and more organic carbon buried in mud on the seafloor. And the changes on the shorter time scales of 10,000 to 100,000 years are associated, again, as David talked about, with changes in the partitioning of carbon dioxide between the ocean and atmosphere. Carbon dioxide obviously goes back and forth between the ocean and atmosphere, but the oceans contain about 50 times as much CO2 as the atmosphere. And so you can raise the CO2 concentration of the atmosphere if you have a mechanism for partitioning some of the ocean's inventory into air, or you can lower CO2 in the atmosphere if you can somehow get it into the oceans. And then the fourth mode of CO2 variations are kind of one-off events, like the Paleocene-Eocene thermal maximum, which is this big excursion 55 million years ago that, again, David talked about. So what I'm going to talk about are, first of all, the long-term timescale constraints, and I'll show you a little bit, talk about what David talked about from a little different perspective, and then look at other events coming towards the present. So this is a diagram similar to the cartoon David showed you, illustrating what regulates CO2 concentration of the atmosphere over millions of years. And as David mentioned, I'll just go through this very briefly, the Earth's interior has a lot of carbon in it, but it's hot. And so that carbon is trying to escape to the atmosphere, just like if you took a rock and heated it up, you'd find that it lost most of its carbon, which was going to be converted to CO2 in the atmosphere. And there's nothing that the atmosphere has to say about the rate of this process. The atmosphere just accepts the CO2 that's being released from the Earth's interior. But the other process is uptake, and I illustrate that uptake in reactions called weathering reactions, and I illustrate that here with a little different equation. Magnesium silicate is a mineral that's common in hard rocks on the Earth's surface. It can be attacked by carbonic acid and dissolved to make dissolved magnesium, dissolved silica, and dissolved bicarbonate. And then, as David said, these dissolved constituents get carried to the oceans by rivers. What the atmosphere does is adjust CO2 to a level where the temperature is just right so that the rate of weathering on the continents removes an amount of CO2 that's equal to the flux of CO2 into the atmosphere by metamorphism, volcanism, and related processes. So one event where this process is relevant, a one-off or two or three-off event, is Snowball Earth, which has happened at least 3 times that we recognized in the sedimentary record. Once was about 2.5 billion years ago, once about 700 million years ago, and once about 630 million years ago. And what seems to have happened is that for some reason the greenhouse gas concentration of air started getting drawn down to lower levels. And as it got drawn down to lower levels, the planet cooled. As the planet cooled, ice covered more and more of the planet and came closer and closer to the equator. And then by the time ice covered about half the surface area of the planet, it reflected so much sunlight back to space that had previously been absorbed, reflected so much sunlight that the planet was unable to maintain any ice-free area. And the rest of the continents and the equator, the rest of the continents and oceans froze down to the equator. So it's very controversial, and the physical evidence is weak, but to me, this is the most plausible scenario. So now we have an Earth completely covered by ice, and that Earth is reflecting almost all of the sunlight that reaches it instead of absorbing that light and energy to heat the Earth. And so the planet keeps itself in this cold state for a long time. But the demise of the snowball happens because volcanoes and other processes are still releasing CO2 out of the solid Earth into the atmosphere. So CO2 accumulates in the atmosphere and accumulates and accumulates. You get a stronger and stronger greenhouse. And after maybe 10 million years, the CO2 concentration reaches a value estimated to be about 300 times its present level. And at that point, the greenhouse effect is so strong that the planet warms enough that you start getting some ice melting. Once the ice starts melting, you have open ocean water, which absorbs more of the sun's heat, and more ice melts, and this process occurs catastrophically until the planet is completely deglaciated. There are enormous amounts of CO2 in the atmosphere, and Earth is now in a hothouse mode. There's one, to my mind, there's one line of evidence that implicates CO2 in snowball processes, and that is that the carbon isotope composition of seawater, as recorded in limestones that deposited during that time, changed drastically. Isotopes, for those of you who haven't thought about this for a while, are simply different atoms of an element with 1 more or 2 more neutrons. But their abundance gives us a lot of geochemical information, and one is that it reflects aspects of the carbon cycle. And what we're going to come to later is one of the things it reflects is how much organic carbon is being buried. So a characteristic of sediments from Snowball Earth is that there are very large variations in the abundance of the carbon isotopes, which signal very large changes in the carbon cycle. Exactly what those are, we don't know, but they would likely have led to large changes in the CO2 concentration of the atmosphere. And this is kind of the string that ties Snowball Earth to the carbon cycle. Okay, now this is another idea, different from the one that David talked about, and I think both are important, another idea for explaining the changes in the concentration of carbon dioxide over hundreds of millions of years during the more recent period of Earth history. So on this axis is time from 500 million years ago to the present. This green line roughly marks the appearance of plants on the continents, which, as David said, changed the geochemistry around, kind of made the continents geochemically modern. And so I'm going to focus just on these last 400 million years. During this period, there were two times of extensive ice ages. One is an event called the Late Paleozoic Ice Ages, where Earth was glaciated, maybe continuously, maybe off and on, for about 90 million years, from 460 million years ago to about 270 million years ago. And then there was another period of ice ages, which we're still in today, which began about 35 million years ago with the glaciation of Antarctica and has become more and more intense through time. And then there was a period from about 140 million years ago to 40 million years ago in which Earth was exceptionally warm. And what I'm going to talk about is hypothesis for explaining these climate variations. And for those of you who have some familiarity with this, called the Blagg hypothesis or geocarb, been pursued by Robert Berner at Yale for many years. So the question is, why did climates change? And presumably, they changed because of CO2. This was a time of low CO2, and high CO2. So why was CO2 high here? This is a picture which I'm sure some of you would have seen of the Zalinger murals at the Yale Natural History Museum. And it depicts the Cretaceous, a time about 100 million years ago when climate was really warm, and you can see all the different dinosaurs are getting along really well, and there's lush vegetation and so on. So why was climate warm? Well, the answer is back here with these volcanoes, that there was a lot of volcanic activity or other processes of the solid Earth that led to especially rapid rates of degassing of carbon dioxide from the solid Earth into the atmosphere. And the atmosphere responded by warming up until weathering removed CO2 at the higher rate at which volcanoes were emitting it. Now, some evidence for this idea comes from this curve of sea level versus time, which is this solid black line here. In this direction indicates higher sea level, and this direction indicates lower sea level. And the idea is that sea level changes for two reasons. One is because ice sheets melt, and the second is basically because the ocean floor becomes shallower. If the ocean floor becomes shallower, it's like you have a full bathtub in your bathroom and you climb in it. What happens? The water overflows. And in this case, the water on this side of the diagram, seawater has overflowed the ocean basins and lapped onto the continents. So what we're seeing here is times when the large areas of the continents were covered by ocean because sea level was higher, because the ocean floor had risen up. Higher ocean floor tends to signify more rapid volcanic activity. It means that seafloor spreading rates are faster, and probably means that other tectonic processes and other volcanic processes are faster as well. And so this link between sea level and climate, which is not perfect, but pretty good, this link between sea level and climate signifies that more CO2 in the atmosphere is a consequence of faster tectonic rates, more volcanism, more metamorphism, and so on. And between that and the question of how much calcium carbonate there is in rocks that are actually being baked by the by Earth's hot interior, those two things together are what seems to be responsible for most variations in the CO2 concentration of the atmosphere over millions of years. Okay, now I said I wanted to talk about the physical evidence linking CO2 to climate. This is one diagram that illustrates that evidence, and you'll see it's, in this case, it's really not that strong. What's plotted here on a time scale from 300 million years ago to the present is the CO2 concentration of the atmosphere inferred from proxies that have nothing to do with ice cores. So these are all indirect indicators of the CO2 concentration of the past atmosphere. And just to give you one example, Dave talked before about stomata, which open up to let CO2 into plants. You might imagine that plants are going to change around how their stomata work if there's a lot of CO2 in the atmosphere or if there's just a little bit of CO2 in the atmosphere. And all the red triangles on this diagram, like here, come from places where biologists have looked at fossil plants and by studying their stomata have made an estimate of how much CO2 was in the atmosphere in the past. And then there are various other, 3 or 4 other indicators people have used to construct this diagram. So can we see evidence for low CO2 here, for low CO2 here, and high CO2 here? Well, I have to say it's kind of equivocal. If you want to see it, you certainly can. And it's encouraging that CO2, that the proxies indicate relatively low CO2 concentrations during the cold times of the last 35 million years. Here, it's harder to say. And here, there's a lot of variability. Some things fit. CO2 is higher during this warm period than during this cold period for most indicators. On the other hand, this time around 50 million years ago was perhaps the warmest time of this interval, and CO2 seems low, if anything, instead of high. So there's a lot of interest in developing other geochemical and plant indicators of past CO2 concentrations and learning more about the links between CO2 and climate. To me, there are 2 events where we have physical evidence closely tying in CO2 and climate. David talked about both of these. One is the carbon release 55 million years ago at the Paleocene-Eocene thermal maximum, and the other is the last 800,000 years where we have CO2 data from ice cores. This diagram pertains to the event 55 million years ago. As Dave said, there are 2 lines of evidence for CO2 release at this time. The first is that the isotopic composition, the ratio of carbon-13 to carbon-12 in seawater changes. And the only way that you can induce that change is by adding a large amount of CO2 from some external source. And the second is that there's physical evidence that the CO2 dissolved in seawater and acidified the oceans, and that's illustrated by this picture of a deep sea sediment core that spans the event. So this is the time before the event here, the time after the event here, and this is where the CO2 release occurred. And what you see is that the mud here, I know this is a little hard, but the mud here is light brown, and then it's dark brown, and then it gets lighter. The light brown color indicates that this mud is mostly calcium carbonate, microscopic calcium carbonate shells with a little bit, they're white, and then there's a little bit of mud worked in. And then the dark color here indicates that most of those calcium carbonate shells have been dissolved by ocean acidity generated by the addition of CO2. And then as you go up in time, a few thousands or tens of thousands of years later, you see the mud getting whiter and whiter and whiter, which indicates that there's less and less CO2 because there's less and less dissolution going on. So this is one time when I think that there's no doubt that there was a climate change caused by CO2. How big was the climate change? Maybe a global warming of about 5 degrees, something like that, which is a lot. It's about twice what we expect from doubling of CO2. In terms of what caused it, my favorite hypothesis is that there was permafrost, that there was no ice cover on Greenland and Antarctica, but there was permafrost. And as Earth was gradually warming, eventually temperatures reached a threshold so that the permafrost started melting, and then bacteria could eat the organic carbon in it and convert it to CO2. I think I'll come to the ice ages. So the green plot is a plot of the oxygen isotope composition of calcium carbonate microfossils from deep sea sediments. And the significance of that property is that it, in a remarkable way, it gives us an idea of global climate in that it depends on high latitude temperatures, and it also depends on the volume of the ice sheets on the continents. So values, green values plotting up here indicate interglacial times, down here glacial times. This is the temperature at Vostok in East Antarctica inferred from the isotopic composition of the ice, and this is CO2 concentration. Analyses of glacial climates indicate that glacial temperatures were about 6 degrees colder than the present, and of that 6 degrees, about 3 degrees is attributed to ice albedo, that is, the ice sheets reflected sunlight and cooled the Earth. About 2 degrees is attributed to lower carbon dioxide concentration during the ice ages, and about 1 degree to albedo of ice-free land. So Earth had more deserts and less forests, and the deserts reflect more sunlight, and the forests absorb more sunlight, as David Schimmel was talking about. And I'd like to finish up by talking about some work that has attempted to relate this CO2 change to global warming temperature sensitivity. And that work is summarized in this diagram. So the plot here, the black line on this plot, which you can see, for example, here, the black line is the same isotopic temperature record as at Vostok. This is the isotopic composition. And the range from interglacial values to glacial values is about 8 degrees temperature change, so colder and 8 degrees warmer. The red line is just the CO2 concentration, and the scale for CO2 is over here, and you can see this remarkable correspondence that David remarked on. And then the blue curve is an attempt to understand the temperature change in terms of two processes. The first of these processes is just the CO2 change. So as the CO2 concentration of the atmosphere changes, temperatures over East Antarctica are going to get warmer or colder. And there are actually two ways in which CO2 changes temperature. First of all, there's the direct radiative forcing. You have lower CO2, a smaller greenhouse effect. And second, there are indirect effects associated with temperature, and with CO2. One example is if you have lower CO2, because temperatures are colder, glaciers extend further around Antarctica, there's more sea ice, and so more sunlight is reflected, and the whole region cools some more because you're reflecting sunlight back into space. There have been 4 modeling studies, which I'll get to in a minute, showing that calculating that the CO2 change led to a change in Vostok temperature of about 5 degrees centigrade. And then the other change is a little more complicated, and that is that Earth's orbit around the sun, as many of you know, is continuously changing. The eccentricity is changing. Sometimes the orbit is circular, sometimes it's eccentric. The tilt of the spin axis, which gives us our seasons, is changing. And the spin axis itself is wobbling around. It kind of wobbles one time every 20,000 years. As a result of these changes, the amount of sunlight that different areas of the planet get during different seasons change. And these seasonal changes also affect temperature at Vostok. But the relationship between that people have invoked between seasonal temperature changes and between changes in Earth's orbit around the sun and seasonal temperature changes at Vostok is kind of complicated. And currently, the best idea seems to be that Vostok is warmest when summers in the northern hemisphere are warmest. And just to give you an inkling of why this might be the case, Vostok gets most of its temperature, gets most of its snowfall during the spring and the fall, not during the summer. And so for Vostok temperatures to be warm, as measured in the ice, you need situation in which springtime temperatures are warm and autumn temperatures are warm. And that comes about when summers are warm in the northern hemisphere. So the second supposition in drawing a synthetic Vostok temperature curve is that when summers are warm in the northern hemisphere, Vostok is about 2 degrees warmer than when summers are cold in the northern hemisphere. And then what this blue curve is just adding the temperature change due to Earth's orbit to the temperature change due to CO2 to get the total temperature variation of Vostok. And you can see that you get a remarkably good fit to the data. You don't get good agreement when the planet is going back into a glacial state. That's the case right here. As you're going from glacial to interglacial, you can see this blue line is way above the estimated temperature at Vostok. But in general, this plan works really well. So it's a plausible explanation for temperatures at Vostok. And then we can ask these models which successfully predict Vostok temperature variations, what do they predict about climate sensitivity? What do they predict about Earth's warming if we double the CO2 concentration? And in a nutshell, these are the 4 different studies that have done this exercise. And in a nutshell, they predict climate sensitivity ranging from about 1.2 degrees warming for CO2 doubling to 4 degrees warming for CO2 doubling. And this is kind of the standard IPCC range. So in summary, I've talked about the reasons for CO2 changes. There are changes due to very long timescale. There are very long timescale changes due to changes in the outgassing of CO2 from the Earth's interior. There are changes associated with, in various ways, with changes in Earth's orbit around the sun. And then there are these kind of unique events which have happened probably only a few times in Earth history that have led to major climate changes, either warmings or coolings. The 2 times that I would say we have really compelling evidence for a link between CO2 and climate are the Paleocene-Eocene thermal maximum 55 million years ago and the last 800,000 years. And evaluating the CO2 climate links at other times is difficult because it's just really hard to get something out of rocks that will tell you precisely what the CO2 concentration was in the atmosphere many millions of years ago. Thank you.